All right, EKG Chapter 6, Interpretation of an EKG Strip. Let's go ahead and see what we're going to talk about. We're going to remember those general rules that we talked about. We're going to describe the basic approach to interpretation. We're going to talk about the 5 steps to identifying these rhythms, and then we're going to explain the heart rate, and then we're going to talk about some causes of artifact. Let's go ahead and get going. Let's talk about some general rules now. So first and foremost, we always want to look at our patient. So you've heard that saying, that trust your patient, not the monitor. So the EKG is just one piece of the puzzle. You have to consider how they're feeling and what's going on clinically when we're talking about our patient. So when you look at the EKG strip, make sure to read it from left to right, starting at the very beginning. So that helps you follow the heart's electrical activity in real time. Now, next, we want to apply the 5-step systematic approach, which we'll go over in this chapter, to analyze the strip. Keeps you focused, organized, so you don't miss anything. And then finally, remember, don't take shortcuts or make assumptions. Every strip is different, and each one requires your full attention to get the correct interpretation. Also, first glance, an EKG strip might seem easy to read, but a quick look can often lead to an incorrect interpretation. So that's why it's so important to ask and answer each question in that 5-step approach that we'll cover. So now sticking to this order is crucial because it helps ensure consistency and accuracy every time that you analyze a strip. And then by following the steps in the proper sequence, you'll avoid jumping to conclusions and get a clearer, more reliable interpretation of the heart's activity. And finally, to really get the hang of reading EKGs, you need to know the parameters for each type of dysrhythmia. So once you've gotten those down, you can apply them to that 5-step approach as you look at the strip. Now this helps you spot the key things like the rate, the rhythm, the waves, all the things, so you can make sure your interpretation is accurate every time. It's all about recognizing the patterns and applying what you know consistently. So here's a 5-step approach that we're going to follow. So what we're going to do is we're going to figure out the heart rate. We're going to determine the rhythm of the heart. We're going to look at the P wave. We're going to look at the PR interval. And then we're going to look at the QRS complex as well. So let's start with the heart rate. So when we talk about the rate of electrical impulses in the heart, we're looking at how many impulses are conducted through the myocardium in 1 minute, so in 60 seconds. So first we have the atrial rate, and that's the number of P waves that you see on the strip. Now each P wave represents an electrical impulse in the atria. And then we have the ventricular rate. So this is the number of QRS complexes that you see. So, each QRS complex represents an electrical impulse in the ventricles. So by counting the P waves for the atrial rate, maybe the QRS complexes for the ventricular rate, you can figure out how fast each part of the heart is firing. Now you remember the SA node normally discharges impulses at a rate of 60 to 100 beats a minute. That's the usual range for a healthy heart. Now bradycardia, if the heart rate is less than 60, that's called bradycardia. So it's slower than a normal heart rate, and it could be caused by a lot of different various factors. Tachycardia, on the flip side, if the heart rate is greater than 100, that's tachycardia. It's a faster than normal heart rate, which can also indicate certain heart conditions. So bradycardia is slow, tachycardia is fast, and a healthy heart usually stays between 60 and 100. Now we've got a couple of different methods here that we can talk about determining the heart rate. So we see that 6-second method, that's a quick way to calculate the heart rate from an EKG strip. So you see there's those little 3 and 6 second tick marks on the top or the bottom of the strip. You'll want to get you a 6-second strip so you can determine this heart rate. Of course you can do it on a 3-second strip, but the math will be a little bit different. Now once you've identified that 6-second window, count the number of QRS complexes, so those spikes that represent the heart's electrical impulses, that happen within that 6-second period. After you've got that count, you multiply it by 10 to get the heart rate for a full minute. So if you count 5 QRS complexes in 6 seconds, you multiply 5 by 10, and that gives you a heart rate of 50. So we can look here, and we can see we have 1, 2, 3, 4, 5, 6, 7, 8. 8 times 10 is 80. So we got a little equation up here, and we see we match. We've got a heart rate of 80. Now there's another method. So you notice that it says it's most accurate if the heart rate is regular, and then it's just an estimation of the heart rate because it's not as specific. So there's this R to R interval method. Now it's another way to calculate the heart rate, and it's especially accurate when the heart rate is regular, as I mentioned. Now to use this method, look for those QRS complexes that fall on a heavy line or the closest to it on the strip, and then count how many large boxes are between that R wave, so the peak of the QRS, and the next R wave. And then once you have that number of the large boxes, you divide 300 by the number of boxes, and that gives you the heart rate in beats per minute. So if we see there's 3 large boxes between the R wave, you would divide 300 by 3, which gives you a heart rate of 100. So here's kind of what we're looking at here. So we mentioned how this whole thing works. We're looking for those QRS complexes that fall on a heavy line, or I mentioned as close to it as you can. The one that I see is this one over here. That's probably the closest. So once we want to count the large boxes between. So 1, 2, 3. We've got 3 large boxes, and this just falls in line with what we talked about. We have 3 large boxes between the R waves, so we divide 300 by 3, which gives you a heart rate of 100. So maybe you want to confirm, you can look and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know by our other way to do it, we can see that that's going to be a heart rate of about 100. Now let's talk about rhythm, or step 2. So think of the rhythm as the heart's natural drum beat. So it's the sequential beating of the heart, and it all starts with electrical impulses that get generated in the heart. So these impulses travel through the heart muscle, telling it when to contract and pump blood. So when we talk about the rhythm, we're really discussing how these electrical signals create just this coordinated and regular heartbeat. So it's what keeps everything in sync, and it just ensures that the blood flows effectively throughout the body. So when you're looking at an EKG strip, you can classify the rhythm based on how the R waves line up. We have regular and we have irregular. So if the intervals between the R waves are the same, so basically like we counted those distances between the R waves, if that is consistent from one side to the other, then the rhythm is considered regular. However, if the R waves don't line up in a consistent pattern with varying distances between them, then the rhythm is considered irregular. So it's all about whether the heart is beating at a steady rhythm or if the beats are a bit more scattered. So here's kind of what we're talking about. We see here we're 1 over the big line. So we go 1, 2, 3, 4, 5, and we can march this one out. 1, 2, 3, 4, 5, same spot. 1, 2, 3, 4, 5. So this looks quite regular. So we know that those R waves, we have the same distance between those 2 R waves as we talk about a regular rhythm. Now, if the intervals between the R waves or the P waves vary by less than 0.06 seconds or about 1.5 small boxes on the EKG strip, we can consider the rhythm to still be regular. So if the differences between the intervals are pretty small, less than 1.5 boxes, means the heart is beating in a consistent, steady pattern. So remember, it requires 1.5 boxes more, or 0.06 seconds, to make it, to consider it irregular. Now let's talk about irregular. So if the intervals between those 2 P waves or the 2 R waves, which is what we were using, vary by more than 0.06 seconds or more than 1.5 small boxes, then that rhythm is considered irregular. But not all irregular rhythms are the same. So there's a few types here. We have a regularly irregular, so that means the irregular rhythm follows a pattern. So even though the intervals aren't exactly the same, they still happen in a predictable way. And then we have occasionally irregular. So here the rhythm's usually regular, but 1 or 2 intervals between the R to R might be uneven. So it's a little blip in the rhythm, but it doesn't happen often. Now, if the intervals between the two R waves vary by more than 0.06 or 1.5, we know it's considered irregular. If the R to R intervals show no consistent pattern at all and have no similarity between them, then the rhythm is considered irregularly irregular. So in this case, the intervals are completely unpredictable and they don't follow any regular rhythm. And we just went ahead and put this one on here so you can, because the examples that were in the book weren't great examples, but you see on this one, Art has it figured out for you, 9 small squares. We see this one is 13. This is atrial fib, which we know, you'll learn is irregularly irregular. And we see 7, so it just goes all over. There's no consistency, no regularity for that rhythm. Now we move on to the P wave. So remember that's that first little bump that you see on an EKG strip. It happens when the right and the left atria depolarize. So basically, when they contract to push blood into the ventricle. So that P wave should be rounded and upright, and its first deviation from the baseline or isoelectric line when you see it on the strip. So that's an important part, rounded and upright. Now when the SA node is pacing the heart and the P wave shows up regularly, it means the heart is firing at the usual rate. So that's what we call a sinus rhythm. It's the normal healthy rhythm that comes from the SA node. So we've already seen what that P wave looks like. Now here's our rules. So our rules on this are the 5 questions to ask as you see it. First off, are the P waves present? So the first thing you want to check is whether you can see P waves on the strip. If there's no P waves, that's an important clue that something might be off. Then step 2 is, are P waves occurring regularly? So next, check if those P waves are showing up at regular intervals. A regular rhythm means the P waves are consistently spaced out, which is a sign that the SA node is pacing the heart properly. Now step 3, is there one P wave for each QRS complex, or is there a QRS complex for each P wave? So this step is about making sure there's a one-to-one relationship between the P waves and the QRS complexes. So for every P wave, you should see the QRS complex afterward and vice versa. So if they don't match up, it can indicate an issue with the electrical conduction in the heart. But hang on, there's more. So step 4, are the P waves smooth, rounded, and upright, or are they inverted? So when you look at the P waves, they should be smooth, rounded, and upright in most leads. If the P waves are inverted, that could be a sign of something abnormal, like if the impulse is coming from a different part of the heart. And then step 5, do they look similar? So do all the P waves look similar? Now check if all the P waves look the same. They should be consistent in shape and size. If they look different from one another, that could suggest there's an issue with how the atria are being activated. So let's take a look here. We remember our rules. So our 5 rules, we're saying, are the P waves present? And when we look at this, we see P waves before each, we see P waves all throughout. And then is the P wave present before the QRS? So we see that 1-to-1 ratio of P waves to QRS. Are they smooth, rounded, and upright, or are they inverted? They're all smooth, rounded, and upright. And then do they all look similar? And these all look very similar. So let's talk about the PR interval. So that's the time interval between, that time interval is called the PR interval. And it's measures the time that it takes from the onset of atrial contraction to the onset of ventricular contraction. So you can measure it by looking at the time from the start of the P wave to the start of the QRS complex. So a normal PR interval should be between 0.12 and 0.20 seconds, which is about 3 to 5 small squares on that EKG strip. So here's our PR interval. So we're looking from the onset until here. So we have 3 questions. Are the PR intervals greater than 0.20? So if the PR interval is longer than 0.20, it could indicate a heart block or a delay in the conduction from the atria to the ventricles. The next one we look at at is, are the PR intervals less than 0.12 seconds? So if the PR interval is shorter than 0.12, that could suggest an accessory pathway. So that's where the electrical impulse bypasses that normal conduction system. And then are the PR intervals constant across the EKG strip? And that the PR interval should be pretty consistent throughout the strip. If it changes, that could be a sign of something like variable conduction. So we're looking at our PR intervals. Are they greater than 0.020? So we see 1, 2, 3, 4. They're all this is within normal limits. They all look pretty they all look pretty consistent across. They're not less than 0.12, so we're still following those rules. And then we look at the QRS complex. So that's electrical excitation of the ventricles. Now the QRS complex, as you remember, that represents the depolarization of the ventricles, which is the big electrical event that leads to the ventricles squeezing and pumping blood. So the Q wave, that is the first negative or the downward deflection in the QRS complex. It's the initial dip that happens before the bigger spike. That bigger spike would be the R wave. Now, right after the Q wave, the R wave is that first upward or positive deflection. It's the tallest waveform on the strip, and it's the one that most stands out in the QRS complex. And we have the S wave. So that's that sharp negative or downward deflection that comes right after the R wave in the QRS. So it represents the final phase of ventricular depolarization, or the last part of the ventricles contracting. So after the tall R wave, you'll see the S wave drop down as the electrical impulse spreads through the rest of the ventricles, and that's preparing them to pump blood. So let's talk about what the three questions to ask here is, which is, are the QRS intervals greater than 0.12? So are they wide? If it's wider than 0.12 or more than 3 boxes, it could mean there's a delay in the electrical conduction through the ventricles, which might indicate a bundle branch block or another conduction problem. And then we ask, are the QRS intervals less than 0.12? So a narrow QRS less than 0.12 typically means the electrical impulse is traveling normally through the ventricles, which is a good sign. And then are the QRSs similar in appearance across the EKG strip? So the QRS complexes should look similar throughout the strip. If they look different, it could indicate there's issues with the ventricles being activated, or that the impulse is coming from an abnormal location. So our three questions: are the QRS intervals greater than 0.12, 0.12? Here's we're talking about our QRS. Looks like we're probably looking at about 1.5 to maybe 2 full boxes. So it's definitely not greater. It's not less than either. And then are the QRS complexes similar? And they all look pretty similar when you look at them. Now we see the ST segment. So this is what we're going to talk about now, the ST segment, and then pay attention to that J point, because we'll also talk about it as well. Now that ST segment begins right after the QRS complex ends and goes until the T wave starts. Now this segment's usually on or near the isoelectric line, which means it's typically flat, and it represents the period when the ventricles are fully depolarized and before they start to repolarize. And then that J point that I mentioned, that's the exact spot where the QRS complex ends and the ST segment begins. It's an important point to watch, because changes in the J point can be a clue for conditions like ST elevation or depression, which can be signs of an MI or some other issues as well. So when you're looking at the ST segment for any elevation or depression, pay close attention to that J point, the point where the QRS complex ends and the ST segment begins. So ST elevation, if the J point is elevated above the isoelectric line, that can indicate myocardial injury or myocardial infarction, so a heart attack. So ST depression, if the J point is depressed below the isoelectric line, it could suggest ischemia, meaning the heart muscle isn't getting enough oxygen, which could be due to conditions like angina and some other medical conditions as well. So changes at that J point can be a very telling sign of these cardiac issues, so we always want to check it closely when we see some ST changes. So once again, I've mentioned it to you, we're very redundant, but here's what we're looking at is our ST. Or that was, now we're headed on to a T wave, sorry, I didn't read the top. So the T wave, that's produced when we start talking about ventricular repolarization, or just that relaxation phase of the ventricles after they've contracted. It's commonly seen as that first upward or positive deflection, and it follows the QRS complex on the EKG strip. Essentially, the T wave represents the ventricles resetting and getting ready for the next contraction. And then sometimes you might see a U wave. It's usually not visible on most EKG strips, and its exact cause of origin isn't fully understood yet, but when it does appear, it typically comes right after the T wave. So it's usually much smaller than the T wave, rounded and upright, so a positive deflection if it's present at all. And then we talk about our last point when we talked about our things we're going to talk about is the artifact. So when we talk about artifact refers to EKG waveforms that originate from sources outside the heart rather than from the heart's electrical activity itself. So these can be caused by various factors such as patient movement, loose electrodes, electrical interference, or even muscle contractions, and we'll talk about these, but artifacts can lead to misleading results, making it important to differentiate them from genuine cardiac signals. So sometimes we'll see some interference on the monitor or the EKG strip that can mess with the accuracy of what you're reading. As I mentioned, the four main causes to watch for: patient movement. So if they move, like shifting around or talking, it can cause muscle tremors that show up as jagged little lines or random spikes on the EKG. Loose or defective electrodes. So if that electrode is loose or malfunctions, they can cause a fuzzy baseline or unwanted noise in the tracing. You'll notice the waveform gets irregular or shaky. And then improper grounding. So if the EKG is not properly grounded, you might see some 60 cycle interference. And that looks like a steady hum or a sinusoidal pattern on the strip, often from nearby electrical equipment. And then faulty EKG apparatus. So if there's something wrong with the actual EKG machine or its wiring, it can also cause some weird artifact or distortion in the readings. So it's important to identify these issues so you don't mistake them for actual heart problems, because it could be very easy to think someone's needing VFib when we see a bunch of artifact, and next thing you know, they're getting electricity. So this just gives you an idea of some sample artifact. It's not uncommon when you're driving down really bumpy roads and things to have some artifact like that. However, we can still identify our QRSs, we can identify our P waves, we can identify, for the most part, our PR interval. So we're still able to kind of look at things and understand, but do everything that you can to get rid of our artifact so you have the best view of what's going on. And there it is, the end. So we'll talk soon.